So first, thank you to the organizers for their kind invitation. I think that's the first time in my career that I'm invited to a tea talk. So thank you. I'm getting coffee though. Just briefly about me, I have two affiliations. I'm sharing my time between Canada and Ireland. I'm a Canada research chair at the University of Ottawa, and I'm a director of a Research Ireland Center for Software Research in Ireland. And in terms of my expertise and area of research, I am at the crossroad of software engineering and AI. And by AI, I don't just mean machine learning. And in two different ways, I work on how to apply AI to software engineering, for example, test automation or requirements quality assurance. And the flip side of that, which is how to adapt software engineering techniques to AI software. So for example, for test automation or in general, assurance of AI-enabled systems. And in fact, I've been using AI, in particular machine learning, from the beginning of my career. But I still remember that when I was doing my PhDs in the early 1990s already, I was actually scolded for using machine learning. That was supposed to be a maverick field that had no respectability. Things have changed. So the objectives of that presentation is to provide a software engineering perspective on the quality assurance and safety of deep learning models and systems. So I'll provide an integrated overview of recent work with students and colleagues. And I will remain fairly at an intuitive level with a few technical details here and there. And because most of the people attending are not specialists and they are not particularly interested in every detail of everything I've been doing. And it's not meant to be a survey, but just a presentation, again, of recent work in which I have been involved. So let me just give you an introduction. So for those in the audience who are not acquainted with software engineering and software testing in particular, here is an overview of key concepts. So the idea of automated software testing is that you want to automatically generate test inputs in a way which is effective at finding faults and in a way that minimizes cost. In practical settings, you have limited resources. And you also want to be able to assess the adequacy of testing, that is whether testing gives you a reasonable probability of finding problems in software. And there are different levels of testing. You can test, developers can do unit testing, and at the opposite end of the spectrum, people can test entire systems. And test techniques are characterized by the information they have access to. Do you have access to source code or not? Do you have access to specification or not? And of course, all those aspects tend to affect how you do automated testing. And once you have tested a piece of software and that you have test results or outputs, then of course, the goal is to automatically detect failures, perform root cause analysis to understand the reasons for failures, use test results to assess the risks in terms of safety or security, and then decide whether or not to deploy software or further debug software, and so on. And of course, one question that people in software engineering have asked themselves for at least the last 10, 15 years is what is the impact of AI? Because obviously it has an impact for a number of reasons. There is no source code that captures a model's behavior. A lot of techniques of engineering were based on program analysis and so on. There are no specifications for ML components. The behavior that is acquired for those components is acquired through training based on data. And models are never perfectly accurate. Whatever you do, this is not going to happen. So you have somehow to be able to deal with it in some other ways. And of course, this has an impact on software engineering technique and methodologies, as you can imagine. But nevertheless, we need to ensure, for obvious reasons, that AI systems are trustworthy. There are several dimensions to trustworthiness. In this presentation, I will focus on aspects related to uncertainty, safety, explainability, due to time constraints. So when you talk about safety verification, ideally, what would you like to have ideally? Absolute safety guarantees, of course, ideally. Practical assumptions in terms of the technique you are using about the input space, the model architecture, the properties being verified. You'd like the technique to be scalable to large models and systems. But in practice, the problem is that you cannot have it all. There is no such technique that satisfies all those requirements. And moreover, properties such as safety properties are model properties, are system properties rather than model properties, which makes it even more challenging. We're talking about the safety of a system, not of a model. So if you look at the research, they are at the high level, there are two realms of activity. Formal analysis, which is based on reachability analysis in neural networks. The focus is on robustness to perturbations, a lot of the research. It can provide guarantees about the models, not the systems, the models, under restrictive assumptions about the model architecture, the shape of the input space, and it's based, of course, on over-approximation of the output space. There are scalability issues. And there is another area of research, which is based on automated testing and using basically search techniques. But it's based on heuristics, obviously. Therefore, there are no guarantees. But on the other hand, there are no restrictive assumptions, and it's much more scalable. And today, we'll focus on the latter area of research because all my research is done in collaboration with industry, and in the end, I need to devise solutions that actually help. So there are different testing levels, but what is important is that in the end, for the reasons I've just mentioned, of practicality and applicability, and not just for AI aspects, testing is still the main practical mechanism through which we gain trust in software, in industry. There are different levels, of course. You can test models, you can test the integration of components. So there are maybe models or typical software components. You can test systems. And they have different objectives in terms of the type of problems that they are targeting. So first, in the first part of my presentation, I'll focus on model testing and analysis. And then in the latter part, I will talk about system testing. Okay. So here is an example of a deep neural network that was used in a system in the automotive industry to detect key points on the face of a driver. That is, the corners of the eyes, the end of the nose, and all that. And the testing was done with a simulator in the loop. And there are many different applications for this that I will mention next. But of course, here the goal of testing was to find a test suite within the test budget that causes the DNN to poorly predict as many key points as possible within that time budget. And the goal was to then evaluate the safety in the context of that system of the model from the testing results. The images were generated by a simulator, so we had a simulator in the loop. There were different example applications. Two common applications were drowsiness detection and gaze detection based on a camera within the car. Obviously, this has many safety implications. I mean, you can't just take chances with such an application. And each key point can potentially be important to any decision that is made based on drowsiness or gaze detection. In our case, we had 27 key points, so we had 27 test objectives on the face. So the goal was to try to find as many mispredictions as possible and diverse mispredictions as possible within the test budget. And we used many objective search algorithms based on genetic algorithms combined with the simulator. I won't go into the details, of course, of that algorithm, but at a high level, we generate inputs using that many objective search algorithms. The simulator generates a test image that is fed to the DNN that predicts the key point positions. And those key point positions are actually compared with actual key point position. And based on that, some form of fitness function is computed in order to further guide the search. And the idea is that we generate critical inputs where the difference between the actual key points and the predicted key points are quite large. So based on doing such a thing, we, for example, simply use the test results with a regression tree in order to predict the DNN accuracy based on simulation parameters. So the simulator, of course, controls a number of parameters about characteristic of the face of the driver, the pitch, roll, and yaw of the head. And this is what determines, of course, the image that is generated. And what we found is that we were able, and you can see it at the bottom, we were able to actually identify very precise rules based on the simulation parameters that predicted accurately the normalized error of the key point prediction. And for example, here you have an example on that image of the rule in the first rule, and here you have an example of the third rule, where here we are quite accurate and here we aren't. And of course, this was extremely useful in order to understand the safety implication of using the DNN. That is, for example, where the situation where the DNN was inaccurate, rare, was that a risk that was acceptable or not? And here, for example, we found out that there were many situations where the DNN was not accurate because there was a shadow on the face. And of course, the DNN cannot do anything about that. It cannot predict key points if there is a shadow covering the key point. So then, of course, what that means is that there are situations where the system has to handle safety. That is, the system has to determine that the model cannot be accurate, and therefore it has to rely on other key points on the face to do gaze detection or drowsiness detection, or it has to do something else. But it cannot trust the prediction of the DNN. So safety has to be handled at the system level. Now you have other situations. For example, what I'm going to talk about here was another project with another industry partner in the automotive industry, where models were tested, but using real images. There was no simulator in the loop for a number of practical reasons that I won't go into. There are also drawbacks about using simulators. So it's not like simulators are the ideal. I don't know what that is. Let me see. Not sure why. No? Should I close this? Yeah. Yes. Oh, maybe I'll just do it again. Yeah, thank you. Here the situation is completely different because typically we have many images that are available, but they are unlabeled. The labeling cost can be significant. I mean, you can't, there are limits to what you can do. Then test selection becomes a very different problem. It's about minimization. It's about selecting within the test budget a subset of images that you're going to label and use for testing. So it's a minimization problem and or selection problem. So we want to test a DNA model with a fixed labeling and test budget. So the idea is how can we automatically select an optimal test subset of inputs to test the DNA in such a way that we maximize our chances of finding problems in the model. And what we do is that, again, we use a multi-objective search algorithm where the fitness functions, as I will show, are based on diversity and uncertainty scores. And the goal is to have a technique that is black box, that is, that doesn't require any information about the internals of the model or even the training set. Because in many practical situations in industry, model training is outsourced. The training data is actually proprietary. But nevertheless, the model that you outsource or that is developed by another division in the company has to be integrated in your system, and before it's integrated, it has to be tested. You have to have reassurances that it won't create too many problems. So the way we deal with it, because of what I said, because in many practical settings we don't have access to the internals of the models, and we still need a scalable and practical solution. Basically, one of the criteria to select inputs that is quite intuitive is that we want to maximize the diversity of inputs in order to exercise the model. And we want to do that in a black box way, as I said. Sorry? What? Ah. Okay. Faut refaire le... Yeah. Okay. Sorry for that.
And then go on the left here. Yes. So here down. Oh. There you go.
Right. Okay. Sorry for that.
And then you can go back to.
Yeah. I managed to. Yeah. Right. So the idea is then to have a black box approach based on diversity that is going to guide the selection of a subset of test inputs that maximize our chances of finding problems in models. The way we measure diversity is that we simply use VGD16, which is pre-trained on a large number of images, in order to extract features from images. And then we measure diversity for a number of reasons as geometric diversity. And what this does is that it takes all the feature vectors and compute the hypervolume of that is captured by all those feature vectors in the feature space. And of course, as you can see, based on that trivial example at the bottom of the slide, the more diverse are the feature vectors, the larger the hypervolumes captured within those feature vectors. And what we do then is Pareto font optimization using, again, a search algorithm, in that case, NSGA2. And we have two objectives on here, diversity, which is the geometric diversity I just presented, and uncertainty in terms, for example, of the Gini score. And the idea here is that we want to trigger as many diverse mispredictions as possible that are caused by different problems in the model. So anyway, we obviously applied that approach on model developed in the automotive domain, and we obtained pretty good results, and the technique could be used by our partner. So there are other issues, of course, is that there are many other contexts where people manually devise test inputs based on expertise or use other ways of devising test inputs. And they obtain good results, that is, the model is deemed to be accurate based on those inputs. But then the question is, can we trust that result? I mean, is that due to the fact that the model, the test suite is incomplete, or is that really due to the fact that the model is accurate? And assessing a test suite to determine whether the test suite is complete is called, in software testing, test adequacy. And how can we assess test adequacy? This actually was a question that was posed to us by another industry partner that was not using the techniques I have previously presented. They just wanted a technique to assess test adequacy regardless of the source of the test inputs. And we want to do that before labeling test inputs. And we want, of course, a technique that is practical, even on for large test suites. And of course, any technique that is going to do that is somehow going to be based on estimating the fault detection capability of a test suite. Because when you want to determine whether a test suite is adequate, you want to determine whether or not it has a high likelihood of finding faults. So we developed a technique, and I'm not going to go into details, but I'm going to walk you through the 3 steps. In the first step, based on the training set, we seed artificial faults in the trained model. What we do, for example, is that we change biases, parameters, weights, and other things. After the model is trained, we compute what we call the mutation detection rate. That is the number of faults that have been seeded that are actually detected by the test suite. And then we move to the next step, where we use basically a nonlinear regression model to model the relationship between the mutation rate and the fault detection rate of a test suite. And we do that on a large number of test suites of different sizes that have been extracted from the training set. And of course, that relationship between the fault detection rate and the mutation score, or the mutation rate, MS here, in the figure, changes a lot from one model to the other. And of course, it depends a lot on the faults that are present in the model, not surprisingly. So that means that relationship has to be modeled, has to be basically mathematically modeled for each DNN. In step 3, then during testing, what we simply do is that we compute the mutation score and we predict the fault detection rate with a certain confidence interval. And depending on that, depending on the results, we decide whether or not the test suite is adequate. And we have obtained a rather, accurate results. And we compared it to alternative ways of doing test adequacy based on coverage metrics, but I won't go into those details. Another important application related to testing models is what I call the differential testing of models. So what is it? It's when you try to generate test inputs that reveal disagreement between models. We call that triggering inputs. And so we developed a specific technique to do that. And why is that important? There are many applications. First, of course, the selection of alternative models. Models, for example, may have similar accuracies, but they are accurate under different conditions. And some conditions may be more important than others. Also, at runtime, given an input, you may actually want to select what is the best model. for that given input. For that, you need to be able to understand under which conditions a model fares better than the other models. So you can, for example, and people do that typically in practice, you can train different models with different architecture based on different training sets and perform that type of differential testing. Also, models evolve, obviously, and you may want to understand the differences between the original and the updated models. Or, as I said, you may want to combine model predictions at runtime. So we developed a strategy to do that. There are two phases or two steps. In the first one, we train a generative adversarial network, or GAN, that attempts, of course, to model the distribution of real images in a given domain. And I'm at Mila. I don't need to tell you how a GAN works, but you have a generator model and a discriminator model, as you know. And the generator models takes latent vectors and inputs that are somehow noise vectors. And then in the second step, we use the GAN to generate images that are fed to the alternative deep neural networks, or whatever the model you are using, that are being tested. And we use two objective search algorithms to generate or to explore the latent space, the latent vector space, in a way that generates diverse inputs that also trigger differences among models. So we have two fitness functions, one to capture diversity and one to capture the differences in predictions across models. So we have demonstrated experimentally that we are very effective at generating triggering inputs and also at generating diverse triggering inputs, that is inputs that show differences between models. And we have also used that in order to understand or model the conditions under which each model was more accurate, so that at runtime people could decide effectively which prediction to trust based on which model. And of course, this significantly improved the overall accuracy of their prediction. Another problem that was posed to us by some industry partner was how to test fine-tuned models. So, as you know, in practice, people develop, let's say, train a deep neural network, and then they try to apply it in different contexts. I mean, the automotive domain, you apply it under different weather conditions. God knows what can happen, but usually a model then is deployed in different contexts. And then the idea is, you don't want to retest from scratch every model that you deploy and fine-tune in a very different context. Because again, resources are limited and you need to somehow, do what you need to do within resources available. And so the question is, how do we test or retest the fine-tuned model? And how do we account for the fact that in different contexts, there are differences in terms of data distributions? And of course, minimize the effort in any case. So if I define the problem, we basically want to rank and select test inputs that come from the environment where the model is being deployed, where the fine-tuned model is being deployed, using its corresponding pre-trained model. We want to take into account that information. Somehow I'll show you how. And we want, therefore, to use the information from both the fine-tuned model and the pre-trained model in order to select and rank test inputs coming from the new deployment environment where the fine-tuned model is going to be deployed. So we develop a strategy. And what we do is that we train a prediction model to predict whether an input is likely to be mispredicted by the fine-tuned model. And we use, of course, those predictions to select and rank inputs. And the features of that prediction model are based on differential testing, which I've mentioned before, that is differences in outputs and also Odin scores to identify out of this distribution inputs, both in the source and the target distribution. And more particularly, the prediction model is using those features. The output of the logic layer of the source model, MS, the output of the logic layer of the target model, the fine-tuned model, MT, the differences between those outputs, also the differences in terms of output labels, and the Odin scores as well from both distributions. So based on that, we were able to, comparing with simpler baselines, to show the effectiveness of the technique and to show that from a practical standpoint, its efficiency was acceptable. And we did very large experiments where we artificially introduced different degrees in distribution shifts in data in order to see how robust were the techniques to different degrees of distribution shifts. Now, in terms of safety, once you have tested such models, at least in the cases where inputs are images, you need to assess somehow to do some form of safety analysis. And what that means is that you need to understand the conditions under which a model fails, even when there is no simulator in the loop. And understanding and characterizing those conditions is not easy. You cannot just look at hundreds or thousands of inputs for which the model misclassified or mispredicted, and by magic understand what are the conditions of failures. So we need to help people identify those situations so that they can devise mitigation mechanisms. And if also we identify those conditions, we can help focus the retraining of the model on those conditions. So we developed an approach to exactly do that. Again, we don't have a simulator in the loop here, remember, that's that situation. And it's basically a black box technique, it's called SAFE, that does not require internal information from the DNN. In the first step, we extract features from the images using, for example, a VGG16, and we perform dimensionality reduction. Why? Because then we perform clustering using a density-based clustering in the case, to cluster similar images in the hope that images within the same clusters have similar root causes for mispredictions. Okay? And in the third step, we select, according to a certain strategy, images from each cluster in order to perform retraining in a focused manner within a certain retraining budget. So at a high level, the experiments with humans have shown that this cluster helped them correctly determine the root causes by only inspecting a few images from each cluster. So therefore, reducing the analysis effort to a large extent. And also retraining based on those clusters was also effective and efficient. Now, I'm going to talk a little bit about system testing. So I'm going to the other end of the spectrum. So you all know about autonomous driving systems. I don't need to tell you about this, but I'm going to use that as an example here, because many of those systems are increasingly relying, especially in the perception layer, on deep learning. So how do we test them? Obviously, it's a challenge, as you can imagine. Like many other autonomous systems in an open context, the scenario space is infinite. I mean, I would say so, We also have difficulties in terms of automatically detecting behaviors that are not desirable. And I'm not just talking about obvious safety violations like a collision. I'm talking about, behaviors that may not trigger safety violation, but that in the long term present a risk. How do we do that automatically? Again, remember, we are in a context where we have no specifications usually. Anyway, you cannot specify an autonomous system in an open context. I mean, it's just not a feasible endeavor. There are also often many safety requirements, for example, because I'm talking about safety here, I'm focusing on that, that you have to deal with. And even if you have a simulator in the loop, which usually you have, you don't have much of a choice for such autonomous system that are safety critical. You need to do a large amount of testing with a simulator in the loop. But even with a simulator in the loop, simulation is expensive, especially physics-based simulation. And therefore, this is a factor that constrains how much testing you can do. So we developed a strategy, again, at a high level, where we use reinforcement learning, and the goal of the reinforcement learning testing the system was to make sequential changes to the environment, in our case, the simulator, in a realistic manner with the objective of triggering safety violations. So we trained a reinforcement learning agent to do so. The challenge was to test many safety requirements at the same time, because we cannot just test a safety requirement and then test a second safety requirement and then test a third safety requirement, and that's just not possible. So what we did is that we somehow combined reinforcement learning with many objective search. And the goal of the many objective search, as you will see in the next slides, is to, at any point in time, select what safety requirement to focus on and what safety requirement is the most likely to get violated at a given point in time. So if I take a very simple example, an air agent, for example, may try to cause the ego vehicle to violate safety requirement by performing a sequence of actions on the vehicle in front of the ego vehicle. And the idea is to steer the vehicle in front, change its speed in such a way that it triggers, for example, a collision. So that's a very simple example. Obviously, in practice, you have many things you can act upon in the environment. So the way that approach works is that the aerial agent in charge of testing performs action in the environment, the simulated environment that contains both the autonomous driving system and the car and environment simulator. It gets rewards, for example, in terms of based on distance between the ego vehicle and the vehicle in front. And it gets information from the state of the environment, for example, about whether or not there was a collision or how close you were to trigger a collision and things like that. And it combines many objective search with reinforcement learning, and in a way that the many objective search algorithm, at every point in time, each time an action must be taken, decides which safety requirement to focus on, because that safety requirement is more likely to be violated. And once a safety requirement is violated, it's removed from the objectives of testing. So you can have here's an example of a simple violation where the vehicle in front is slowing down abruptly and at the same time steering to the right. And somehow the model must not have been trained for such situations, and there was a collision. So you can imagine when you look at this, and this was based on a very competitive ADS with a very realistic simulator. But you can imagine that finding that type of problems is like finding a needle in a haystack. So if you just randomly run scenarios, you are very unlikely to find them. A problem, as I said, is that simulation is very expensive. So people have been trying to use so-called surrogate models. using different sets of techniques that I briefly mentioned at the bottom, that mimics a simulator to a certain extent, while being much less computationally expensive. And it may not be perfect, those algorithms may not be perfect, but they are so much quicker, and that in the end, they allow you to find more problems, makes your testing more effective. We more recently attempted again to find a solution for system testing of AI-enabled systems, but we took a quite different tech for reasons I will explain. The main reason is that our goal was not just to find safety violations, it was really to find more subtle, undesirable behaviors that may not have led to a safety violation, but that nevertheless were very important to detect. And we used basically we adapted some techniques from software testing that I will mention. We used first a more sophisticated evolutionary algorithm called cooperative co-evolutionary algorithm for reasons I will mention, and something in testing called metamorphic testing. And I explain what that is very quickly. So it's testing that is based or steered by differences in system behavior when you vary inputs, when you vary test inputs. So basically, it's based on the notion of metamorphic relation, and I'll give you an example. That is, what is the expected relationship in outputs when you modify inputs in a certain way? So an example is that if you have two identical scenarios, but the second scenario is only different in one way, it's that at some point the pedestrian crosses the field of view of the car. You don't know what should be the speed of the car in both scenarios. You don't know in the second scenario to which extent it should slow down or whatever. But what you know is that at some point, the speed in the second scenario should be lower than in the first scenario. And if that doesn't happen, then there is a problem. But it helps you not having to determine for hundreds of thousands of test scenarios what should be the expected behavior. You only have to specify what should be the changes in outputs when certain changes in inputs take place. And it's much more efficient from a test automation standpoint. So, yeah, here is an example of what I just said. It's a bit slow, but it should eventually work. Where you have exactly the same scenario on the left and the right. But you will see that if it starts, you will see that on the right-hand side, at some point, the pedestrian is crossing, but the car doesn't seem to affect the speed of the car. There may not be a collision with the pedestrian, but it doesn't affect the speed of the car. And probably the model was somehow disturbed by that red truck standing in the middle of the road there. So instead of detecting the pedestrian, it detected the truck somehow. So we use co-evolution algorithm. I'm not going to go into detail, but basically, you probably know about evolutionary algorithms. And co-evolutionary algorithms are basically algorithms where you divide the search space into subspaces, lower, therefore, the dimension of the search spaces, and it enables parallelism and more efficient search, but it's not easy to use, and it's not easy to adapt to specific problems. In our case, we had a search space of scenario and a search space of perturbations where we manipulated various attributes, added, deleted, or replaced objects in the driving scenario. And of course, the objective here was the violation of metamorphic relation. And of course, the diversity of the test scenarios. But it goes without saying, we don't want to generate constantly similar test scenarios. It has no benefit. So we wanted to generate diverse scenarios leading to as many violations of metamorphic relations as possible. The results is that we significantly outperformed simpler forms of search in detecting metamorphic relation violations. It was much more efficient, much faster. We had high scenario diversity, but interestingly, what we did is that we took a large sample of violations. We showed that to ADS experts, and we asked them to tell us whether or not this was a safety issue, a serious safety issue. And their feedback confirmed that indeed, yes, even though safety violations were not observed, those undesirable behaviors captured by metamorphic relations were actually undesirable behaviors, potentially leading eventually to safety problems over time. So, just checking time. So, I may skip the next part in order to maybe get a bit more time, but for discussions. But another area is that we worked on actually reinforcement learning agents, testing and runtime monitoring. Maybe I'll go through quickly. Why? Because we worked again for a partner in the automotive domain that was using such a reinforcement learning agent, or at least trying to use it, I should rather say, for lane merger on highways, helping the driver with merging on lanes when entering the highway. And didn't work very well, but that's another thing. So before we could work on testing and runtime monitoring, we actually had to improve the agent quite a bit because you know, it was not very difficult to test when we got it the first time. Let's put it that way. We found many problems quite quickly. But anyway, so you know about reinforcement learning. I don't need to tell you about it. But people, surprisingly, even though it's not that easy to use, are increasingly trying to use it in mission critical or safety critical domains. But you know, training an agent to maximize reward doesn't in any way prevent potential safety problems. So you need to basically test the agents and understand when they work and when they don't work. And anyway, at runtime, once they are deployed, you need to monitor them, as I will mention quickly. So we developed basically a strategy, but I'm going to go quick on this, where first we developed a rigorous testing and strategy that is fully automated to detect what we call episodes that lead to dangerous situations. And we also developed a technique for continuous safety monitoring at runtime in order to try to predict violations sufficiently in advance so that the system can take some corrective measure or preventive measure to avoid catastrophes. For the testing part, there are 3 phases. First, we run the agent in the test environment and generate many episodes. We label many of those episodes in terms of functional faults. And during the second step, we basically train an ML model to predict faulty episodes. What I mean by episodes, maybe I didn't mention that, sorry, is that we characterize each input of the reinforcement learning agent as an episode, which is a sequence of pairs state actions, if you will. So we try to identify, to learn, to predict faulty episodes. To do that, we need to use some form of state abstraction. We can use the concrete states of the agent because we will not be able to learn anything. So we use a form of state abstraction in order to enable more effective learning of that predictive model. And I will explain what a state is and what state abstraction is in the next slide. And once we have done that, we actually use that model as a fitness function in order to search for faulty episodes, and then characterize the conditions that lead to faulty episodes. So the way we deal with fault extraction, here we use Q-learning for the RL agent, or we assume that the RL agent is based on Q-learning, and we use a Q-irrelevant state abstraction, which basically, in that case, a state is the Q values for every action in a given state. Okay, so that set of Q values, which basically captured the expected reward, represent the state. And of course, then you can assume that every vectors of Q values that is different is a different state, but then you are not going to be able to train any predictive model. So we use basically an abstraction technique that considers, determines when, based on an abstraction, when two states are equivalent. And D is basically for a given agent determined empirically. And once we have done that, then we are able to predict, faulty episodes, and we use that at runtime for trying to predict safety violations sufficiently in advance. That approach, again, is based on set abstraction and building a prediction model. And without getting into details. So that's what we did. And it worked pretty well. We got pretty good accuracies, and we were able, basically, on average, to predict safety violations about halfway through the episodes at runtime. So we still had on average half of the episode left before the violation manifested itself. So to summarize what I've presented, I talked about testing, analyzing, and retraining the models with or without simulation in the loop. Here we focused on images as inputs and prediction and classification with DNNs, at least in the presentation. We focused also on understanding the differences between DNN models in order to smartly combine them, for example, at runtime, or understand which model to select. Also, I talked about efficiently testing fine-tuned models. I talked about testing systems with safety as a system property, and how to perform in different contexts safety analysis. And also, very briefly, how to deal with scalability, for example, through surrogate models for simulators, or using co-evolution algorithms to make search more efficient. What I've not addressed are things like simulation fidelity, if you have a simulator in the loop and the simulator is imperfect, like it is usually the case. What are the consequences? And how do we deal with this? Models where inputs are not images. Many of the techniques I've presented somehow assume images as inputs. Other properties and safety, which I have not talked about. And how we deal with generative models as opposed to things like regular, quote unquote, deep neural networks. There are other related work I haven't talked about, like determining the safety boundaries of an AI-enabled system, safety monitoring of line components using safety metric forecasting. So there are many other pieces of work I could have covered here, but that I chose not to. And you can see the references. Thank you very much.
Is there any questions?
Hi, great. Thanks for your talk. I have a question about the Carla agents. We've worked a lot with Carla. What is the brain of the Carla agents?
The what, sorry?
What kind of brain, what is the controller of the individual cars in the Carla environment? Is it like the the built-in rule-based methods, or do you have like an actual
Oh,
policy? running?
you're asking me about how Carla is designed because you are referring to whoever used Carla?
Well,
yes.
use Carla in a number of different lines
Yes.
of work,
I
and
think this might be Carla.
for example, yeah, this one, this is a good one. So is it, what's controlling the car? Is it a rule-based algorithm, or do you have a policy that's learned to control the car?
I mean, I did not design the car, just using.
Okay, so you're just using whatever's built into Carla.
I need, when you do testing with the simulator in the loop, you need somehow high fidelity simulator. It doesn't matter what the technology used to build the simulator is. What matters is that you're able to control it, able to control what you need to control.
Right, but you're not modifying the control policy of the car. is what
No,
you're-
no, no, no. Yeah, no. We are testing the automated driving system, autonomous driving system. But you have the automated driving system sending comments to the simulator. Okay,
Okay.
and getting feedback from the simulator.
Right, but like in Carla, you can, there's the simulation and then there's the brain for the car. And it's not clear to me if you're tweaking the configurations of the cars or if you're also
yeah,
altering
here,
the policies of the
yes,
cars.
here it's not just the car, it's also the environment.
Mhm.
Like the vehicle in front, for example.
Mhm.
Uh,
So do you change the initial configurations of the cars and then induce
Yes,
the accidents?
yes.
Or do you,
Yes, you change the configuration of the simulator and then you run. That's how you run the test case.
okay.
But there are two things: you have the simulator and the autonomous driving system. We are testing the latter. I'm not testing the simulator. But of course, the simulator may be also imperfect. That's why I talked about.
But is the brain of the car, the automated driving system, one that's provided by like the industrial partner, or is it the one that's built into Carla?
I know Carla is not provided by the industrial partner.
Yeah, but Carla.
But the ADS, yes, that's the system under test.
Right. So the ADS is provided by the industrial partner,
yes.
and it's running inside of Carla.
Yes,
And then
yes.
you're
Carla already on the simulator, but we use Carla because that was our best option.
right.
It doesn't matter what is a simulator, you know. I mean,
Right. Okay, so your approach is really tweaking the configuration parameters of the Carla setup and
Yes.
the ADS parameters that are exposed to you. Like the ADS system is kind of a black
yes,
box.
Yes, and the idea is to trigger safety violations or other milder form of undesirable behaviors in the ADS.
Mhm.
Yes.
Right, but the ADS is effectively a black box too.
Yes, yes, because yeah. Though because it's not like we don't have access to the internals. Well, it depends on the situation. Those are different projects. Sometimes people don't have access to it, but it's just that we need something that is scalable and practical. You know, also, so we don't want to do a complex analysis of intervals of the ABS to be able to devise the test cases.
Okay, thank you.
So here the analysis has been mostly focused on images. Have you also like experimented with LLMs, for example?
I'm working on that right now, but problems are very different. The problem is whether LLMs can be toxic or misrepresent facts. It's much more complicated than mispredictions or there are other challenges. The inputs and the outputs are much more complex. So, but that's something I'm working on right now with a company that does customer care software. LLM agents handling interactions and requests with a customer. with a human agent or not, depending on the state of the discussion. And then of course they are worried about, providing incorrect facts or their undesirable outputs. But it's not something that I chose to cover today because it's too early.
Yeah, I was just curious if there is some overlap between this work and what you're doing.
I think there are many other challenges with LLMs. Testing is much more expensive, and the input and outputs are much more complex. And detecting problems, what I call the test oracle or the mechanism to detect problems, in the outputs is more complex. How do you detect that facts automatically that facts are misrepresented? It's not obvious, because you don't want to do that manually, obviously.
Thank you.
I don't hear the microphone, sorry. Just speak louder and I will.
Thanks for that. I want to know, do you consider is it present, but the response time of the model is
Yes, you're right. And actually, that's why complex models that have long inference time actually are a problem for testing, obviously, because they limit your testing resources even more. But in terms of testing for inference time, I guess that's what you're talking about, then you could use similar strategies, but instead of trying to maximize fault detection, you try to maximize inference time, I guess. But I would say that this is more of a problem for LLMs.
Let me check once more online. Okay, we don't have questions. We have no more questions. Thank you again, Lionel, for the talk.
Thank you very much. Bye.